All right, the next test that we're going to learn is the integral test. The integral test, unfortunately, requires you to integrate. The first thing you must check is the function needs to be positive, continuous, and decreasing after some point. It doesn't always have to be positive, continuous, decreasing. If there's a couple terms that aren't, as long as it happens after some point, we're good. But what happens is if it's positive, continuous, and decreasing, that the integral and the series will converge or diverge together. They don't have the same sum or the same value, but we know if one of them diverges, which means infinity underneath the area, or the series sums to infinity, then the other one's also going to diverge. But if one of them is finite, the other one is also finite. We have two ways we can show decreasing. One, we could take the first derivative and show that it's less than 0 after some point, or that the next term is always less than the previous term. So in the first one, of course, when we first started this, we didn't know about p-series, but some of you probably already do now if you're rewatching this. This would be a p-series, but before we knew that, we knew it was positive and continuous. Positive because we're plugging in values like n equals 1, n equals 2. All of these values would be positive. Continuous because the only place it's not continuous is when the denominator is equal to 0. We're not looking at that because the first one we're going to use is 1. So it is decreasing. So that means I can look at this limit. So I'm going to integrate from 1 to infinity, which is an improper integral. So we take the limit as we get closer to infinity, so b approaches infinity. We integrate. We resubstitute. And remembering what the natural log looks like, that is a curve that has an asymptote and then goes up at a very slow rate, but it is going up to infinity, so this does diverge. Since the integral diverges, which means that the value is infinite, that means the series will also diverge. That if we added all of these, it would also have an infinite sum. Second one. Again, showing it's positive, continuous, and decreasing. So all we have to do is look at this integral. This is the integral of arctangent. And remember, arctangent is lazy tangent. He's on his side. He's half asleep in class. He has asymptote here and here. And we know where that asymptote is because originally it was sine over cosine, and cosine is 0 at pi halves. So we know that's approaching pi halves. Because remember, the inverses are not the inverses. Yeah, the inverses are the graphs are reflections about y equals x. So if you knew the graph for tangent, you can get the graph for arctangent. And same things with the next two. Here, positive, continuous, decreasing. You got to do a little u substitution, but you can see that that is a finite value, so therefore the integral also converges. On the fourth one, I meant to put a 2 right here because the natural log of 1 is undefined. So you can see that if we go through that, the series does converge. So there's your integral test.